Good day. I am going to report the subcategories of displacement reaction. So there are three categories of the displacement reaction. First is the hydrogen displacement. The second is the metal displacement. And the third is the halogen displacement. So what is hydrogen displacement? So the hydrogen displacement is all alkali metals and some alkaline earth metals like calcium, strontium, and barium. So, which are most reactive of the metallic elements will displace hydrogen from cold water. Then, many metals, including those that do not react with water, are capable of displacing hydrogen from acids. For example, zinc and magnesium do not react with cold water but do react with hydrochloric acid. As you can see in the figure shown below, the zinc is a reactant which is present to the left of the reaction arrow. Now, this chemical equation describes a redox reaction. Here, zinc metal is being oxidized to zinc cations. On the other hand, hydrogen is being reduced by hydrogen's ions to hydrogen gas. This can be seen by looking at the oxidation states of the atoms involved in the reactions. So notice that zinc goes from an oxidation state of 0 on the reactant side to an oxidation state of +2 on the product side, which means that it is indeed being oxidized. So hydrogen goes from oxidation state of +1 on the reactant side to an oxidation state of 0 on the product side, which means that it is reduced. Therefore, we can say that zinc is acting as a reducing agent because it reduces hydrogen to hydrogen gas while being oxidized in the process. So hydrochloric acid, the compound that delivers the hydrogen ions to the reaction, is acting as an oxidation agent because it oxidizes zinc to zinc cations while being reduced in the process. As well as goes to the second chemical equation. The figure below shows the reaction between hydrochloric acid and the iron, zinc, and magnesium. So these reactions are used to prepare hydrogen gas in laboratory. As you can see in the figure below, the A here is the iron, and the B is the zinc, and the C is the magnesium with hydrochloric acid to form hydrogen gas and the metal chlorides. So the reactivity of these metals is reflected at the rate of hydrogen gas evolution, which is slowest for the least reactive metal, which is the iron, and the fastest for the most reactive metal, which is the magnesium. So next, we have the metal displacement. So a metal displacement is a metal in a compound can be displaced by another metal in the element state. So an easy way to predict whether a metal or hydrogen displacement reaction will actually occur is to refer to an activity series, sometimes called the electrochemical series. So as you can see in the figure that's shown in the right side of the screen, that is called the electrochemical series. So basically, an activity series is a convenient summary of the results of many possible displacement reactions similar to the ones already discussed. So as you can see in the figure shown here, from lithium to sodium, it reacts with cold water to produce hydrogen. Then the second, from magnesium to cadmium, it reacts with steam to produce hydrogen. And third, from cobalt to hydrogen, it reacts with acids to produce hydrogen. And the last one is from copper to gold, do not react with water or acids to produce hydrogen. According to this series, any metal above hydrogen will displace it from water or from an acid. But metals below hydrogen will not react with either water or an acid. In fact, any metal listed in this series will react with any metal in a compound below. For example, zinc is above copper, so zinc metal will displace copper ions from copper sulfate. So, metal displacement reactions find many applications in metallurgical processes. The goal of which is to separate pure metals from from their ores. For example, vanadium is obtained by treating vanadium oxide with metallic calcium. So as you can see in this figure shown below. Similarly, titanium is obtained titanium chloride according to the reaction, as you can see in the figure that's shown in the screen. So in each case, the metal that acts as the reducing agent lies above the metal that is reduced, that is calcium above vanadium, and magnesium is above titanium in the activity series.
Halogen displacement. So, another activity series summarizes the halogen's behavior in halogen displacement reaction. So, if 2 greater than is 1 is 1 to greater than Br2 greater than 1 to. So, the power of this element as oxidizing agents decreases as we move down group 7A from fluorine to iodine. So, molecular fluorine can replace chloride, bromide, and iodide ions in solution. So, in fact, molecular fluorine is so reactive that it also attack waters. Thus, this reaction cannot be carried out in the aqueous solution. So, on the other hand, molecular chlorine can displace bromide and iodide ions. So, in aqueous solution, the displacement equation are C C12 G plus 2 KBBRA close parenthesis cube AQ close parenthesis. So to K CI C1 close parenthesis A AQ plus BR to 1. So muna ang formula. So the ionic equation are C1 to G plus 2BR AQ to 2C1 A AQ plus BR2 ay 1. So C1 to G plus 21 AQ to 2C1 AQ plus 1 to. So molecular bromine in turn can displace iodide ion in solution. Br21 plus 2I AQ to 2BR plus 2 plus 1 to. So reversing the roles of the halogens, this halogens produces no reaction, thus bromine cannot displace. So chloride ions and iodine cannot displace bromide and chloride ions. So next, the halogen displacement are reaction have a direct industrial application. So the halogens as a group are the most reactive of the non-metallic elements. So they are all strong oxidizing agents. As a result, they are found in nature in the combined state with metals as halides and never as free elements. Of these four elements, chlorine is by far the most important industrial chemical. In 2008, the amount of chlorine produced in the United States was about 25 billion pounds. So making chlorine the 10th ranking industrial chemical. The annual production of bromine is only 100 that of chlorine, while the amounts of chlorine and iodine produced are even less. So recovering the halogens from the halides requires an oxidation process, which is represented by 2x to x2 plus 2. So where x donates halogen elements, seawater and natural brine, for example underground water in contact with salt deposits, are rich sources of C12Br2 and I2 ions. Minerals such as fluorite, CaF2, and cryolite, Na3AIF6, are used to prepare fluorine. Because fluorine is the strongest oxidizing agent known, there is no way to convert F2 ions to F2 by chemical means. So the only way to carry out the oxidation is by electrolytic means. Industrially, like chlorine is produced electrolytically. Bromine is prepared industrially by oxidizing Br2 ions with chlorine, which is a strong enough oxidizing agent to oxidize Br2 ions but not water. So 2Br AQ to Br2 I plus 2. One of the richest sources of Br2 ions is the Dead Sea, about 4,000 parts per million ppm by mass. All dissolved substances in the Dead Sea is Br. Following the oxidation of Br2 ions, bromine is removed from the solution by blowing air over the solution, and the air-bromine mixture is then cooled to condense the bromine. So iodine is also prepared from seawater and natural brine by the oxidation of I2 ions with chlorine, because Br2 and I2 ions are invariably present in the same source. So they are both oxidized by chlorine. However, it is relatively easy to separate Br2 from I2 because iodine is a solid that is springly soluble in water. The air blowing procedure will remove two of the bromine form but will not affect the iodine present above in the activity